Welcome back to the Chem OG. Today we're going to take a look at sugar linkages. And so sugar linkages, or what are called glycosidic bonds, are bonds between individual sugar molecules. Now, if we want to be successful at naming a linkage, there are two important skills that we're going to have to learn. The first one is being specific about which carbons exactly are involved in the linkage, and that means we're going to have to give our carbons numbers. So understanding how to name carbons in a linkage is going to be very important. And because sugars, when they cyclize or when they form a ring, they can take on a couple of different forms. We need to be able to specify which of the anomers, the alpha anomer or the beta anomer, is the one that's used in the linkage. So those are the two primary skills that we're going to be focused on today, which are figuring out which carbon numbers are in the linkage itself, and figuring out which anomer of the sugar is the one that made that linkage in the first place. So numbering carbons is what we're going to start off with, and numbering carbons has a few rules. The first one is whatever carbon you identify as carbon number 1, it can only be bonded to one other carbon. And if you think about it, the reason it can only be bonded to one other carbon is because otherwise it's not really carbon number 1. If the carbon that we're looking at is bonded to 0 other carbons, that means that there's no chain of carbons to begin with. It's kind of by itself. If the carbon that we're talking about is bonded to 2 other carbons or more, that means it's in the middle of a chain. It's not at the beginning of a chain. And so the only way that it makes sense for us to identify a carbon as carbon number 1 is to make sure that it's bonded to only one other carbon, and that's pretty much it. Now, when we do start numbering our chain, sometimes we may have a couple of different options in terms of where it is that we can start numbering. And so whatever you do, you want to make sure to identify the most oxidized carbon first. And we mean that in a biochemistry sense for sure. We're looking for the carbon that's bonded to oxygen the most number of times. And then once you figure out which carbon that is, try to start your chain, or you need to begin your chain, as close as you can to that most oxidized carbon. So those are the rules. Let's try to apply them. So let's take a look at a molecule like glucose. Okay, so whether it's D or L is something that we've already covered in another lesson, and like I said, whether it's alpha or beta is something that we're going to take a look at shortly. But what I want to take a look at now is just getting our bearings together and figuring out where carbon number 1 is going to be. So whenever you have a ring like this, it's tough to figure out where your ring should begin and end. But remember that carbon number 1 can only be bonded to one other carbon, and that gives me two distinct options. I can start numbering at this carbon over here. That's one of the carbons that's only bonded to one other carbon, or I can start numbering at that carbon all the way on the left over here. That's another possibility for starting my chain. Any other carbon in this molecule is bonded to at least 2 other carbons. So where am I going to begin my chain? Well, I need to start as close as possible to the most oxidized carbon. And that most oxidized carbon is this one right here. That is the only carbon that's bonded to oxygen twice. If you take a close look at any of the other carbons in this molecule, there's no other carbon that's bonded to oxygen more than once. So that is the only carbon that's bonded to oxygen twice. That makes it the most oxidized carbon. I need to start my chain as close as possible to that carbon. So that means that that is going to be carbon number 1 and not the one on the left. Now, where's carbon number 2 going to be? Well, because carbon 1 is only bonded to one other carbon, there's only one direction in which this chain can go. So that means I need to head downward in order to find carbon number 2. Carbon number 3 is right next to that. Carbon number 4 is right next to that. Carbon number 5 is right next to that. And then finally I end up with carbon number 6. And so notice that that other carbon that I was looking at as a possible place at which I can start numbering my carbons ends up being at the other end, or at the end of the chain. So there you go. We just numbered all of our carbons on glucose. Let's take a look at another molecule. So let's take a look at fructose as well. Okay, so glucose and fructose are the two main sugars in honey, which was on the beginning of our video today. So if we take a look at fructose, let's check out where our possibilities are in terms of numbering. So I only have this carbon right here is bonded to one other carbon, and this carbon over here is also bonded to one other carbon. But remember, we want to take a look at the most oxidized carbon, find that out first, and our most oxidized carbon is this one. It's the only one that is bonded to oxygen twice. So notice that that carbon is not at the beginning of a chain though. It's bonded to one carbon here and one carbon here. So that means it cannot be carbon number 1. So I'm going to start numbering as close as I can to that most oxidized carbon. And that means beginning at that carbon all the way to the top right. And then continuing my chain all around until I get to carbon number 6. So it's not always the case that the most oxidized carbon is carbon number 1, but I need to make sure that it's as close as possible to the beginning of my numbering, that most oxidized carbon. All right, so now that we took a look at numbering our carbons, we're ready to go next level and make sure that we understand which anomer is involved in a linkage. So what's an alpha anomer and what's a beta anomer? Well, your alpha anomer is defined as when the oxygen that's in the linkage is on the opposite side of the ring or trans with the last carbon in your chain. So for example, we took a look at 2 molecules earlier that had 6 carbons in them. The last carbon in the chain is carbon number 6 for those molecules. If we only have a 5 carbon chain, then it would be carbon number 5, and so on and so forth. So let's take a look at one piece of glycogen. Okay, so glycogen is a whole bunch of glucose molecules that are connected together in all types of different fashions. And what we want to do is we want to identify the linkage that's in this little snippet of glycogen that we're looking at. And so I'm going to begin by numbering carbons. So I'm going to take a look at the portion over here on the left. This carbon is only bonded to one other carbon, and it's bonded to oxygen twice. So that's a pretty good candidate for carbon number 1. Now, if I take a look at the oxygen over here that's in this linkage, I notice that this oxygen is on the opposite side from carbon number 6. So if I continue numbering right on down the chain, this would be carbon number 1, this is 2, this is 3, this is 4, this is 5, this is 6. This oxygen is on the opposite side of the ring from carbon number 6, which means that what I have here is the alpha anomer of the sugar on the left. Now let's take a look at the sugar molecule that's on the right. If I take a look at this carbon is bonded to not just one carbon up top here, but it's also bonded to another carbon down here as well. So that means it cannot be carbon number 1. And so what I need to do is I need to take a look at where the most oxidized carbon is, and that happens to be right there, and it's only bonded to one other carbon, so that means that that's carbon number 1. And if I continue down the chain, that's carbon 2, continue down the chain, that's carbon 3, and then finally I get to the carbon that's in the actual linkage, then that is carbon number 4. So that means that this particular linkage is known as an alpha 1,4 linkage. So it's alpha because it was the alpha anomer that was locked into this particular bond over here, and it was carbon number 4 on my other molecule that was included in that linkage as well. All right, what about the beta anomer? Well, the beta anomer is when the oxygen in the linkage is cis or on the same side as that last carbon. So let's take a look at an example of that. So when we take a look at sucrose, here's what we got. I got the sugar that happens to be on my left side here, right? And the carbon that's in that linkage, this one right here, is the most oxidized carbon, and it's bonded to only one other carbon. So that has to be carbon number 1. Now, if I take a look at the other side of my linkage, what do I have? Well, this carbon is the most oxidized carbon, but it's not carbon number 1 because it's bonded to the carbon that's up top, and it's also bonded to the carbon that's down here. Now, before we get ahead of ourselves, let's take a look at the type of linkage that we have on carbon number 1. This oxygen is down in the ring. It's on the opposite side of the ring from the carbon that's last in the chain. This carbon is up in the ring. This oxygen is down. So that means that I have the alpha anomer of the molecule on the left. Now, Let's take a look at this molecule. Well, we want to number our carbons as close as we can to this most oxidized carbon. So that means that that carbon up top is going to be carbon number 1, and the carbon right underneath it is going to be carbon number 2. Now, which anomer is the one that's involved in this linkage? Well, the oxygen is down here, but then the last carbon is this carbon on the chain, right? If I number, I got 1, 2, 3, 4, 5, 6. This carbon down here is the one that is also down in the chain, and it's on the same side of the ring as this oxygen. So that means I have the beta anomer of the molecule that's on the right-hand side. So glucose is on the left, fructose is on the right. What's happening is that the bond is between carbon number 1 on an alpha glucose and carbon number 2 on a beta fructose. So this linkage actually combines the alpha anomer on one side with the beta anomer on the other. Notice that for the molecule that we had from before, we didn't really specify the anomers on both. We only specified the anomer on one, and that's because the second molecule could flip its anomer, whereas here, both of the anomeric carbons, and that's just a fancy way of saying that the most oxidized carbons, both of the oxidized carbons happen to be in the linkage together, and that's why we have to specify the particular anomer on both. But for the other molecule, it was carbon number 4 that was involved, and that wasn't an anomeric carbon. So we took on a couple of really complicated examples. Now that you know how to number your carbons, you don't need to only take a look at sugar molecules anymore. So let's take a look at examples in biochem that go beyond, sugars and carbohydrates only. So here's an example of two molecules. On the left, I got ribose, and on the right, you'll notice that it's pretty much the exact same molecule, but this is deoxyribose because we're missing that hydroxyl group over here. Now, you have the ability to be able to figure out which carbon number is the one that's missing that hydroxyl group, or where the deoxyribose gets its name. And so if I take a look at my most oxidized carbon, it is this one over here. It is bonded to only one other carbon, so that means it is carbon number 1. And that means that the hydroxyl group is missing on carbon number 2. So deoxyribose is missing that hydroxyl group at carbon number 2. And deoxyribose versus ribose should automatically ring a bell with you as being the difference between RNA and DNA. And so let's take a look at an example of 1 unit of DNA. So if I take a look at an example of a unit of DNA, stop me if you've heard this before. DNA replication happens in a 5' to 3' direction. But now you have the ability to figure out what those numbers mean. And so if you take a look at the carbon that's at the beginning of the chain over here, that's our most oxidized carbon. Now, here it's not bonded to 2 oxygens, it's bonded to an oxygen and a nitrogen, and those are 2 things that are more electronegative than carbon. So that indeed is the most oxidized carbon in that ring. And so the next one down the line is going to be carbon number 2. Now notice I put little prime sign next to there. So what's 1', what's 2'? How come all of a sudden we're switching our numbering here instead of being just 1 and 2, being 1' and 2'? Well, by convention, what happens is when we refer to numbering in nucleic acids, we usually start by numbering with what's up top here in the whatever it is that we have, whether it's a purine or pyrimidine. We use our numbering here first, and then the primes refer to the carbons that are in that particular ribose. And so we got 1', we got 2', we got 3', we got 4', we got 5'. So that's where 5', 3', and so on and so forth, that's where they come from. When we talk about replication that's happening here, it means it's happening from 5' on down to 3' until you get to the next nucleotide and so on and so forth. Thank you so much for watching today's video. If you have not done so yet, please subscribe to this channel. We absolutely welcome your support. We hope you found today's information helpful, and if you did, please hit the like button. See you next time.